5.5 Determinants and Cramer's rule. The determinant of a 2 by 2 matrix. We actually learned this formula when we were doing cross products with vectors. So if your 2 by 2 matrix is A, B, C, D, the determinant of A, or sometimes the notation for determinant is those straight up and down lines, the determinant of A, B, C, D is equal to AD minus BC. For a 1 by 1 matrix, A equals one entry A, then the determinant is just that singular entry. For number 1, evaluate the determinant of A. The determinant of A is AD minus BC, so 6 times 3 minus 2 times negative 3. That would be 24. The determinant of a square matrix. If A is an n by n matrix, then the determinant of A is obtained by multiplying each element of the first row by its cofactor and then adding the results. The minor Mij of the element Aij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. The cofactor capital Aij of the element little aij is negative 1 to the power of I plus j times the minor Mij. What in the world does that mean? Number 1 is referring to when we would delete a row and column to find the entries of the 2 by 2 matrix determinant we needed to multiply by in order to find the cross product. In order to find the cross product, the first row would be ijk, and the sign for j was always minus. That's because of the sign of this cofactor element. So the sign is negative 1 to the I plus j. For example, if you're talking about the entry in the first row, first column, A11, then I is 1 and j is 1. If you plug those in, negative 1 to the 1 plus 1 is negative 1 squared, which is a positive. That's why the first sign is positive. But for A12, when you plug in 1 and 2 for I and j, it's going to be negative 1 to the 3, which results in a negative. And that's why we subtract that second term. What about for A13? That will be negative 1 to the 4th, which is again positive. When you continue doing this with the I and j numbers that correspond to the entries, you'll find the signs alternate and are plus minus plus, minus plus minus, plus minus plus. Number 2, evaluate the determinant of the matrix. Expanding along the first row, the signs will be positive, then negative, then positive. The constants in the first row are 2, 3, and negative 1. We'll multiply each of these constants by a 2 by 2 determinant. The entries of each of these determinants are the entries obtained by deleting the ith row and the jth column. In this case, deleting the first row and the first column. We get 2, 4, 5, 6. Our second determinant entries are 0, 4, negative 2, 6. And the entries of the third determinant are 0, 2, negative 2, 5. Now evaluate the determinants of each 2 by 2 and simplify. The determinant of A is negative 44. Part B. Now evaluate the determinant by expanding matrix A by the second row. So for cross products, we always had the first row was ijk, so we always expanded across the first row to get the resultant vector. But we have all constants here, no ijk. We can actually expand along any row or any column that we want to. Expanding along the second row is nice because it has a 0 in it, which saves us some time in evaluating. So if I expand along the second row, the signs are negative, positive, and then negative. The numbers are 0, 2, and 4. Multiply each of those numbers by a 2 by 2 determinant obtained by deleting the row and column that those constants came from. So 3, negative 1, 5, 6, 2, negative 1, negative 2, 6, and 2, 3, negative 2, 5. Evaluate the determinants and simplify. Wow! Again, the determinant of A is negative 44. For part C, evaluate the determinant of A, again, by expanding by the third column. The signs for the third column are plus, minus, and plus. The numbers are negative 1, 4, and 6. And your determinants are as follows. 0, 2, negative 2, 5. 2, 3, negative 2, 5. 2, 3, 0, 2. Evaluate and simplify. And again, you get negative 44. So I think negative 44 is the determinant of A. Invertibility criterion. If A is a square matrix, then A has an inverse if and only if the determinant of A is not equal to 0. For number 3, show that matrix A has no inverse. They didn't even tell me which row or column I had to expand upon, so I'm going to choose the second row because it's got a lot of zeros. You could also choose the third column. I can obtain the signs of the cofactors of a 4x4 matrix the same way I did for a 3x3. And guess what? It alternates just the same. So my signs will be negative, positive, negative, positive. The constants are 0, 0, 0, and 3. Now each of these constants will be multiplied by a 3x3 matrix, but the ones that are multiplied by 0 will just become 0. So I'm left with 3 times the determinant of this 3x3, 1, 2, 0, 5, 6, 2, 2, 4, 0. I'm going to expand this 3x3 determinant by the third column because it has 2 zeros in it. The signs for the third column are positive, negative, and positive. The constants are 0, 2, and 0. And remember, it doesn't matter what the determinants are that are multiplied by 0 because those will just be 0. So I'm just going to fill in the one for 2, which is 1, 2, 2, 4. Don't forget, this is all multiplied by 3. I can multiply the 3 and negative 2 in front since they're both scalars and then find the determinant. Oh my goodness, the determinant is 0, so A has no inverse because the determinant of A is equal to 0. Let's talk about Cramer's rule. To develop the formula for Cramer's rule, solve for x in the system below. To solve for x, I need to eliminate the y's. So I'm going to multiply the top equation by d and the bottom equation by b, and then subtract them. Both of the terms on the left side have an x, so factor that x out, and then divide both sides by AD minus BC. X is equal to RD minus BS over AD minus BC. Similarly, we can solve for y and get y is equal to AS minus CR over AD minus BC. Cramer's rule for systems in 2 variables. Given a system of equations where the coefficients are a, b, c, d, and the equations are equal to r and s, the system has a solution x is equal to the determinant of RBSD over the determinant of ABCD, and y is equal to the determinant of ARCS over the determinant of ABCD, as long as the determinant of ABCD is not 0. Using the notation below, we'll call D the coefficient matrix, the 2x2 coefficients of x and y. dx will be the 2x2 matrix where we replace the coefficients of x with r and s. And dy is the coefficient matrix where the coefficients of y are replaced by r and s. Then x is equal to the determinant of dx divided by the determinant of d, and y is equal to the determinant of dy divided by the determinant of d. Number 4, use Cramer's rule to find the solution to the following system. R is -1 and S is 2. The coefficient matrix is 2, 6, 1, 8. For dx, replace the x coefficients with r and s, -1 and 2. For the dy matrix, replace the y coefficients with r and s, -1 and 2. Now evaluate the determinants. X is equal to the determinant of dx divided by the determinant of d, so -20 over 10, which is -2. And y is equal to the determinant of dy divided by the determinant of d, so 5 over 10, which is 1/2, making your solution -2, 1/2. Number 5, use Cramer's rule to solve the system. For a system of equations with 3 variables, we'll do the same thing for Cramer's rule, but it will just be a little more complicated because we have larger matrices to find the determinants of. The coefficient matrix is 2, -3, 4, 1, 0, 6, 3, -2, 0. Remember, the equals column 1, 0, 5 will replace the coefficients of the variable in each specified matrix. So for dx, 1, 0, 5 replaces the first column, the x column, in the coefficient matrix. For dy, 1, 0, and 5 replace the y column. And for dz, 1, 0, and 5 replace the coefficients for the z column in the coefficient matrix. Let's evaluate the determinants of each of these matrices. For the determinant of the coefficient matrix, I decided to expand along the second row since there's a 0 and a 1. The signs of the second row are negative, positive, and negative. The numbers are 1, 0, and 6. Remember, 0 times anything is 0, so I don't need to figure out that 2x2 determinant. Now find the determinants and simplify. the determinant of the coefficient matrix is negative 38. For the determinant of dx, I decided to expand along, again, the second row because it has two zeros in it. Remember the signs are negative, positive, negative, so that 6 will be negative, and I'll ignore where the zeros would be. The 6 is being multiplied by the 2 by 2 determinant 1, negative 3, 5, negative 2. Evaluate. And the determinant of dx is negative 78. For the determinant of dy, I also expanded along the second row. And got negative 22. And for dz, I definitely expanded along the second row. Which simplifies to be 13. So in the formula, x is equal to the determinant of dx divided by the determinant of d. So negative 78 over negative 38, which is 39 over 19. Y is equal to the determinant of dy over the determinant of d. So negative 22 over negative 38, which reduces to be 11 over 19. And z is equal to the determinant of dz divided by the determinant of d, 13 over negative 38. So the solution to this system of equations is 39 over 19, 11 over 19, negative 13 over 38. Those fractions look crazy, and I can imagine that solving using Cramer's rule here rather than Gaussian elimination is much simpler. What else can determinants do? Determinants can help you find the area of a triangle given 3 points on a coordinate plane. The area of the triangle is equal to plus or minus 1/2 times the determinant of the matrix, where the x values of the vertices are in the first column, the y values of the vertices are the second column, and the third column is just ones. Why is it plus or minus? Because area should always be positive until we get to calculus. So choose the sign that ultimately makes the answer positive. Find the area of the triangle below. First, label the vertices and plug them into the formula. To evaluate the determinant of this 3 by 3, I decided to expand along the third column. The signs for the third column are plus, minus, plus. The numbers for the third column are 1, 1, and 1. And here are the 2 by 2 determinants. Evaluate the determinants and simplify. Because I have a negative 12, I multiply by negative 1/2 to get a result in a positive area. Wow, the area of this triangle is 6 units squared. And what is a determinant? I highly recommend you watch this video to find out more.